Okay, so maybe let's start. Good afternoon, ladies and gentlemen. What I would like to do in the second lecture today is to address a question that has been sort of discussed strongly and controversially for a long time, namely the issue whether superfluidity can still exist in a regime where there's some long-range ordinate density like you have in a crystal. I mean, this question has been discussed first in the context of helium-4, where actually turns out the answer is negative. It doesn't exist in solid helium-4. But I mean, the question came up in recent years, in the last 2 years essentially, mainly in the context of dipolar gases. And I will actually sort of in the last part of the talk say something about dipolar gases and also about some recent work which I've done together with Johannes Hoffmann on that. But of course, I will try to, in a way, introduce the question in a hopefully pedagogical way. And I start out by asking the question in a very provocative form, actually in a form which Tony Leggett used in a paper in 1970, namely, can a solid be superfluid? If you pose it in this form, it's a contradiction itself. And the superfluid is, by definition, also a fluid, and the fluid is not a solid. So clearly, the answer to this question, I mean, put in naive form, is no. Now, we will see the answer to this question can be yes, if we are willing to sort of make our notion of a solid a bit more wide in terms of, say, a mass density wave, as I will explain. If this is something you call a solid, then the answer is yes, you can have a supersolid. And this is something that actually, I think, became clearer with the work on cold gases and dipolar gases in particular in the last 2 years. So historically, the first to ask this question was Penrose and Zwerger in their paper on long-range order and the connection between long-range order and Bose-Einstein condensation. And they immediately dismissed this possibility. They said, well, a solid is something where particles sit on certain given places, but we know that in a way off-diagonal long-range order, long-range phase coherence requires particles to be delocalized over the whole sample. The only thing that could be delocalized in a classical solid are defects, in, vacancies, or interstitials. But those, as Zwerger and Penrose argued, are thermally activated. So at lower temperatures, they always freeze out. And so they said, OK, no coexistence of a solid and superfluidity. Now, this is, of course, based on a somewhat naive perception of a solid in terms of a classical sort of periodic array of marbles put into a lattice friction. If you think about it in a more quantum mechanical form, like, I mean, these are quantum particles. They can exchange their places. They can hop from place to place. If there are bosons, they can also sit twice at one place, and so on. And so in principle, it's not completely unimaginable that maybe by quantum mechanical tunneling, a particle, even in a solid, could sort of delocalize over the whole solid. It's not, I mean, this is not outrageous. In particular, a very simple version of this has been promoted by Andreev and Lifshitz in an influential paper in '69, where they said, well, imagine that we have holes in a solid, say, like he called them defectons, where essentially you have what I call an incommensurate solid. The number of atoms is either larger or smaller than, by finite density, of course, the number of lattice sides. Then, for instance, this hole I have there can, of course, by tunneling and hopping, go through the whole crystal, and it could be could form a long-range. There could be long-range phase coherence, and so Andreev and Lifshitz said, well, yes, this is a possibility. They did not really, I mean, they speculated a bit about helium-4, but they didn't, I mean, make any sort of specific, I mean, microscopic estimates. But what they did is something quite remarkable. They said, well, if you have something like this, so you have a finite density of such defects, even in the ground state, then there will be a new mode. You have an additional broken symmetry. compared to the usual solid, and there's a new mode. And what they said is that diffusion of defects, which you always have in any solid, as one of the hydrodynamic modes of a solid. So if you count the number of hydrodynamic modes that are there in a solid, just from the number of broken symmetries, then it turns out defect diffusion is always 1. That was understood only in the 70s, precisely by Paul Martin, for instance. This defect diffusion is then, as Andreev and Lifshitz had predicted, replaced by some, if you wish, wave-like propagation instead of defects instead of diffusive motion. Now, Leggett, in a paper with the title, as I noted above, a year later said, well, maybe, but note that, I mean, such a supersolid, as they called it at that time, is certainly a pretty fragile phenomenon, because what he argued is, and what he showed by actually sort of a, well, rigorous, if you wish, inequality, he showed that the fact that the density, the real particle density, is no longer uniform, but is modulated, that sets an upper bound on the superfluid fraction. We have seen that, or I've argued, that the superfluid fraction in a fluid, superfluid, in a Bose-Einstein condensate is actually 1 at 0 temperature, is perfect superfluid, but that was based on the assumption that the density is uniform. If the density is not uniform, Leggett has actually given an upper bound whose explicit expression I don't give here, but in a way, qualitatively, what it shows is sort of the formula I've given here, namely you can introduce a visibility for the density, just the usual type of visibility, sort of n max minus n min divided by the sum as a function of the density. And imagine a situation like the one indicated here on this figure on the right, where you have essentially, I mean, particles, the density is really has sharp peaks at a regular lattice of sites, and there is hardly any density in between. Such a system has visibility close to 1, exponentially close to 1, because of sort of exponentially small densities in between. And then what this inequality gives you is then essentially an exponentially small, of course, superfluid density. So it's a pretty fragile phenomenon. And of course, what you also conclude from this argument is that, okay, the more interstitial density you have, the better it is. That's something that, I mean, okay, intuitively is more or less obvious. Okay, good. So let's, I mean, in order to avoid any ambiguities, what I mean by a supersolid, because I mean, people are taking different definitions and so on, I will start out with a definition, what I think a pretty wide one, but not absolutely, so it doesn't include everything, definition. Namely, I define a supersolid, quote unquote, by the fact that it shows this off-diagonal long-range order, so this phase coherence I explained sort of last lecture, together simultaneously with and now be cautious, an interaction-induced modulation of the density. So the density should not be externally imposed by some whatever means, I will come back to this, but it should be sort of a consequence of interactions between the particles themselves, but it should be, of course, a real modulation of the density, and it should coexist with this long-range order. So that's, of course, a reasonable definition of a supersolid, which I will use. But then you see already this definition is in a way general enough as to include, for instance, the old good enough vortex lattices. I mean, that have been realized in the context of ultracold gases in 2001 and 2005, respectively, at MIT with BECs or Fermi gases near the BCS-BC crossover. The picture is taken from the latter, where you nicely see sort of a triangular array of vortices, each carrying h over m as a unit of vorticity. And this is a system which is clearly a superfluid and clearly has a modulation of the density. At the dip of these vortices, density is reduced, is almost going to 0. And so clearly it is consistent with the definition above. Note, by the way, Abrikosov in 57 has predicted such a state. There, nobody talks about a supersolid clearly. Well, because there, I mean, the electron density in a type 2 superconductor is completely flat, although sort of course, the order parameter, superfluid order parameter, has the same type of modulation. But here, in cold gases, also there's a density dip. So there's a periodic density and superfluidity coexisting, so it's a supersolid, if you wish. Well, of course, it's not the one which people would have liked to see, and which sort of there was such a heated debate over decades. And one thing or an essential thing which distinguishes this one from the supersolids people have looked for is that in this situation, there's only a single order parameter. It's the order parameter of the superfluid order parameter itself, which is spatially modulated. So it's a spatially modulated superfluid, or maybe a superfluid crystal, as you would like. But it does not have, and this is what people had looked for, two independent order parameters. And so in particular, you would, I mean, for a genuine supersolid, you would keep the periodic order even if after superfluidity is lost. This here, I mean, if you have your vortex lattices and you go above the critical temperature of BC, then of course also your vortex lattice is gone. But of course here, what we really want to have for a supersolid, for a full supersolid, is one where we have a superfluid phase, perhaps even here in this regime of solid helium above the critical pressure, where you say maybe this melting line is just a line where a periodic density appears, but maybe superfluidity goes up a bit higher. That was, in a way, what people had speculated for a long time. Now, what I will show, or argue at least, is that this doesn't happen. In helium-4, the solid helium-4 is essentially a Mott insulator. That's not superfluid, definitely not. But you can have a supersolid in the above sense with an interaction-induced periodic modulation of the density, these dipolar gases, where, of course, now the solid phase is a mass density wave, is incommensurate. Now, in order to make my points, I try to be sort of reasonably pedagogic and start out with an example that I think most of you know pretty well, but which is, according also to my definition, not a supersolid, but it teaches us quite a bit about, in particular, the old Andreev and Lifshitz idea of sort of, in a way, defects being important for supersolidity. So I will start out with cold atoms in an optical lattice, where actually the periodic order is exposed externally, and discuss, I mean, what this has to do with this Andreev and Lifshitz mechanism of supersolidity. And then I will say a few words about sort of the roton instability in helium-4, and then also compared to that that appears in dipolar gases. We'll say something about a criterion which goes back to Hansen and Vallée on freezing, which I think reasonably general, and then in the end discuss about this issue I mentioned before from Andreev and Lifshitz. How can you understand sort of the new mode that appears and in terms of a wave-like propagation of defects. Now, as mentioned, a model which, okay, is a toy model, although not a real supersolid, is a BEC in an optical lattice that was realized now 20 years ago by Markus Greiner, Immanuel Bloch, Olaf Mandl, Tilman Esslinger in the group of Ted Hensch in Munich, where you put a Bose-Einstein condensation in an optical lattice. And you see that cranking up the depth of this optical lattice, you go from a phase in which this Bose-Einstein condensate is really coherent over the size of your sample to a situation where particles essentially like to sit at given places. So they go to a Mott insulator. The microscopic Hamiltonian, which, I mean, faithfully describes that, is this Bose-Hubbard model, as was pointed out by Dieter Jaksch and Peter Zoller, Ignacio Sirac, and co-workers, where they essentially say you have bosons moving in the lowest band of a periodic potential with some dispersion, which, okay, is usually used to be of the tight binding form. And then there's some local on-site repulsion. If more than one atom occupies a given site, you pay some energy U. So that comes from just the short-range scattering length. And you regulate the density with the chemical potential. Now, if you have negligible interactions, which essentially means that the width of the band, which I call B, this is the bandwidth, is much larger than this on-site interaction, then, I mean, this is superfluid. And in the limit where the U is really very much smaller than the bandwidth, this is just sort of an ideal BEC in an optical lattice. And the ground state is just sort of the Bloch state at zero quasi-momentum occupied as many times as you have your particles. That's a very easy situation. So this is on this phase diagram on the right side. B over U is, well, much larger. And then if you crank up the chemical potential, then, I mean, the density, of course, also increases. And out there, I mean, well, further to the right, actually, there's a simple mean field relation between the chemical potential and the average density, namely mu is U times average density. So you reach density 1, which means 1 atom per site at mu equal to U. This is sort of this dashed line. You reach density 2 up there and so on. If you now go increase your interaction and follow the lines of constant density, then they look like this. I mean, actually, sort of be cautious with this figure. This figure is done, is plotted for a situation where the bottom of the band is always independent of the hopping at zero energy. So the line here, which separates the vacuum state from a finite density system, is always at the same, is always at zero chemical potential. And so this line of fixed density goes a bit down. And then eventually, sort of, if the U becomes large enough, then particles cannot delocalize anymore, and there's a Mott insulating phase. And this is a Mott insulator with either unit filling or 2 particles per site and so on. And what you may or may have been surprising to you when you, I mean, most of you, I think, have seen this phase diagram, is that if you are at a density, so if you would have a uniform system and you give a density, and the density is not precisely an integer, then the system actually stays superfluid down to the lowest hoppings. That's following, if you follow a line where sort of the density is, say, 1 minus epsilon, some 0.05. Then the line of constant density sort of is a bit below, but then sort of goes around this Mott insulator, because the Mott insulator has integer density. That cannot enter the Mott insulator. So this line has to go down below the Mott insulator, and it ends only sort of asymptotically in this point. If you are a bit above, it goes above this point. So this was already explained in the old paper by Fischer et al. On this model. And it's essentially Andreev and Lifshitz. Why? Well, because if you, and this is what I wrote here, any sort of Bose crystal with a finite defect density means sort of a bit above or a bit below unit filling, is a supersolid. So that's a signature of, I mean, in this phase diagram of the Andreev-Lifshitz mechanism, the fact that the superfluid phase sort of hits sort of essentially zero, goes down to zero bandwidth hopping is a consequence of the fact that at any density which is different from an integer filling, you can delocalize the rest of your particles in a way easily. Now, of course, this is a system where sort of the real density, if you ask about the real particle density on a microscopic level, not on a level averaged over a single site as you see in single site resolution. Of course, in single site resolution images, you see the density averaged over a single site. I now really want to have the density on a microscopic scale. That varies a lot. And the Leggett bound implies that the superfluid fraction in the system, even in the ground set, is not 1. And actually, you can show that in the limit where sort of the interaction is weak, you can express it in terms, essentially in this, the Leggett bound, you can express the Leggett bound in terms of the ratio of the bare mass divided by the band mass. So if your optical lattice is pretty deep, I mean, this mass to the band mass is pretty small. So the superfluid fraction of this superfluid, even out there, is small because there is a deep density modulation. Now, density and, of course, superfluidity are sort of completely different beasts. I mean, density order is trivial in this situation. I mean, in the superfluid, it's just sort of in the limit of weak interactions, n times the Bloch wave function, single particle Bloch wave function at zero quasi-momentum, which, if you express it in terms of the Wannier functions localized around lattice sites, is just the sum of these Wannier functions squared. If you go to a mod insulator at the same integer density, it's essentially the sum of the squares. And if these Wannier functions are reasonably well localized, I mean, there's not much of a difference. Of course, both densities are periodic. There's long-range order in the density. I've imposed it externally. But, I mean, there's not much happening in the density. It's pretty a boring difference. The mod insulator has a density which is quite similar for deep optical lattices with the superfluid phase. Of course, it's completely different. In the momentum distribution, you are sensitive to, in a way, the long-range order in the amplitudes for particles, and this is what I discussed last time. Essentially here, you have the overlap of you take a boson out at the origin, or you take a boson out at some distance side r, and I mean, these two states have a finite overlap. If this is true, then, of course, this lattice sum then adds up coherently, and it gives a number NL times a Kronecker delta at each reciprocal lattice vector, and it gives a momentum distribution which in the uniform system would scale like the square of the number of lattice sites. And the prefactor here is the condensate density. You measure essentially the condensate or condensate fraction. So these pictures which show with increasing depth of the lattice the appearance of these Bragg peaks, their increase, and finally sort of their disappearance, in a way is measuring, ideally speaking, a state which you show has a large or reasonably large condensate fraction. And you get something, you measure long-range order in the amplitudes, and the superfluid phase has a condensate fraction which eventually goes to 1, while the the superfluid fraction is much less than 1. And we'll come back to, I mean, what the physical consequences of the small superfluid fractions are. Now, one thing you can ask also in this context is, I mean, maybe how can I go if I have a commensurate sort of solid phase? How can I get out of it? That's, I mean, and could I get to a superfluid? I mean, what are the conditions for that? That's also something that, I mean, upon looking at this phase diagram, you can understand. The mod insulating phases are phases where there's an integer number of particles per, on average per site. Of course, it's not a local Fock states. These are not local Fock states. There is, of course, virtual transitions where sort of a particle hops to another side and so on. But these, in a way, local defects or interstitials that may appear, they are bound. They cannot be free. So in a way, to get out of one of these mod insulator states, they have a finite width. So the width is the vertical, delta mu in the vertical direction here. Of course, near the transition, this width goes to 0. And you can always, so this is the difference between sort of the upper line mu plus and the lower line mu minus. And you can, and this is discussed in the old paper by Fischer, you can write this width as a sum of two positive quantities, namely a quantity which is the energy sort of to add a particle or to energy to get out a particle, delta particle plus delta hole. If you are sitting in somewhere in the middle of this mod insulator, I mean, the only way you can change your density and then go to a superfluid up there or down here is that you provide sort of either sort of this delta P or the delta H. And a transition requires that either the energy to add a particle or the energy to remove a particle vanish. That's the only way to get that. Now, for instance, in this simple Bose-Hubbard model, you can easily check that, I mean, this delta H down here at small hopping behaves like mu minus b, so it vanishes precisely at a mu equal to b at a very small bandwidth. Vanishes, and so this shows that the line here starts with a linear slope 1 in this unit. Now you can, in a way, of course, make a big jump. I go from sort of this Bose-Hubbard model where I imposed my lattice externally. I say, well, I mean, can I compare this, or can I relate this to solid helium-4 where I have a commensurate crystal? And for solid helium-4 is, although of course it's a strongly interacting system, I mean, since it's bosons, it's amenable to really microscopic calculations. And these energies, the delta P and the delta H, have been calculated by Prokofiev, Svirstanov, and Bonin-Zeniu some time ago. This was in the discussion of the old Kim and Chan experiments. They thought maybe they had seen supersolid helium-4. But what they show is that, I mean, these energies are, I mean, 20 or 13 Kelvin, so relatively high at the low temperatures which are relevant for that. And so this means, so if you wish, you essentially sit somewhere a bit below sort of the middle of one of these mod insulators. You have to go a pretty long way to add particles to this, or to remove particles and get out. But I mean, so solid helium-4 from this perspective, or is a mod insulator, and you're not, there's no way. You would need to tune your interaction such that one of these guys vanishes. But okay, the interactions in helium-4 are not so. They don't do that. One final remark in this context. So generically, to have a supersolid, you need an incommensurate density. I mean, on a set of zero measure, you can also have, if you wish, a commensurate supersolid. So the original idea in this context where I said maybe sort of the old Pensaber-Onsager argument is incorrect, even if I have a commensurate solid, maybe particles could sort of move around by tunneling, is not excluded. But it is essentially, you would to have a super fine tuning of your conditions microscopically. You don't get that generically. It would be sort of the line of integer densities here on this side. So it's possible. Okay. Let's, in a way, discuss a bit the story of helium-4 again, and also the issue of the roton instability, because this plays a role also in the context of the dipolar gases, which I will talk about later, and in particular also understand in a way what is the difference. Why does sort of the situation in helium-4, crystallization in this case leads to a commensurate mod insulator? It leads to a state which is not supersolid. Now, in helium-4, if you are on the liquid side, a famous approximation due to Feynman, which I will also discuss in the next lecture, is the so-called single mode approximation, which tells you that the excitation spectrum is obtained from the free particle excitation spectrum just by dividing by the static structure factor. And the static structure factor, I mean, is given here. It shows a peak as sort of typically for liquids. In fact, the peak is pretty is not much pronounced. You see the peak goes up, I mean, static structure factor as a dimensionless quantity goes up to 1.4. And if you undergo the transition from liquid helium above Tc to below Tc, it actually goes down even a bit, which is somehow intuitively easy to understand, because I mean, the superfluid transition sort of in a way delocalizes your particles, and therefore sort of order in space, which is described by this peak in the static structure factor, is actually reduced. And then, I mean, if you use the Feynman approximation, and here I'm using results from a paper by Franco Dalvovo, Sandro, and some French collaboration on density functional theory of liquid helium-4, where they were able to explain the experimental data on the spectrum quite well, and the Feynman approximation is off by a factor of 2 roughly, so this is this upper curve here. So it's not quantitatively valid, but it is something that, of course, was the original motivation of saying, okay, there is why there is this rho-tone minimum in the excitation, because there is a peak in the structure factor. And if you look at where the position of this peak is, that's sort of, I mean, at Q's, where essentially, I mean, the 2 pi over Q is the interparticle, average interparticle spacing. So basically, the minimum appears at sort of when particles really get close to on the order of distance. But now if you say, I mean, if I go from the liquid and I want to go from the liquid to the state with a finite density modulation, so just increasing the pressure, I mean, the question is, I mean, does this rho-tone minimum change a lot and sort of perhaps go down? No, it doesn't. If you look at the data for this excitation spectrum between saturated vapor pressure here and 25 bar, which is near the transition, it has hardly changed. And at the transition, the rho-tone minimum is still finite. The transition is a first order transition. So there's at a finite value, if you wish, in this single mode approximation of the peak of this, the system jumps to a state. Now a criterion which connects the static structure factor to freezing, starting from the liquid phase, was developed actually in the context of classical liquids by Jean-Pierre Hansen and Luc Verlet in the old times in '69, actually by doing computer simulations on classical liquid and for classical fluids with strong short-range repulsion. What they found is that, of course, the freezing or melting line depends on pressure and temperature, but all along this line, essentially, it turns out that the critical, so this is taken from their paper, we then obtain a simple law of crystallization by stating that it should occur when the major peak in the static structure factor reaches a value of 2.85. So basically, it means that sort of if you, I mean, whatever, cool down a system, then sort of this peak goes up, but when it has reached a critical value of order 1, then you jump to a first order transition. That was Hansen and Verlet for classical fluids in 3 dimensions. It had actually been checked later on by Bardi, and Eugene Demmler is sort of the last author of this paper. They've shown that, I mean, even for quantum fluids, a similar criterion holds. So they have tested quantum fluids with different interactions, long-range interactions, rather short-range interactions, bosons and fermions, and have looked at where do these quantum fluids freeze into sort of periodic order. And what they found is that sort of the critical value of the static structure factor at this peak is considerably smaller than the classical Hansen-Verlet criterion, but it appears in a regime which is relatively independent of the precise details of the interaction and also even the statistics of the particle. You note also here they plotted the position of this maximum in units of the essentially average interparticle spacing. You see they're always sort of the same order. So this means that if you have transitions driven by repulsive interactions, where, I mean, the peak appears near average interparticle spacing, you get first order transitions at a criterion which, I mean, can be obtained from just looking at the static structure factor. But you end up, in the end, in all these cases, you end up with sort of commensurate mod insulators. So you're not producing states which have a finite density of defects in their ground state. And now this is the situation. Now I come sort of to the dipolar gases. That's different now, of course, for cold gases. Otherwise, of course, you wouldn't be here to talk about supersolids. Now the dipolar gases, of course, so far, I mean, have been realized with magnetic dipoles. And the interaction is most conveniently, so these dipolars are all oriented in the same direction, say the z direction. called the dipole moment d. And the interaction is, can be written as the dipole moment times the magnetic field. Say you have one dipole at the origin and another dipole at point x, and then you have the product of the B, which is created by a dipole at the origin, magnetic field at point x, which is created by a dipole at the origin. So that's, now it's convenient to actually look at this in Fourier space. In Fourier space, we know the magnetic field must be linear in D and must have zero divergence by Maxwell. That's the only function you can have. And this is actually, I think, well, this is important because this part for magnetic point dipoles, it's different for electric dipoles. This part for magnetic point dipoles also contains the interaction which causes all the hyperfine splitting of S states, which we know quite well. So that's important. So if you dot it in, you see by Cauchy-Schwarz, that's always negative. So you see the dipolar interaction, of course, is, so in Fourier space, it's very simple for magnetic point dipoles. And you see it's always negative. It's directional dimensions, but it's always negative. So you immediately see that, I mean, this is bad. I mean, dipolar gases per se, if this is alone, then, I mean, the stuff is unstable. Effectively, you can say this describes some system with, I mean, an effective scattering length, which is minus a so-called dipolar length, and the dipolar length is proportional to the dipole moment squared, which, of course, you want to be as large as possible in the and also it's good, for instance, to have a large mass to get the dipolar moments large. So if you have a three-dimensional homogeneous system, the fact that such a dipolar gas is actually stable requires you that you have an S-wave scattering length which is larger than this. Otherwise, this system isn't stable. Things are a bit better if you sort of confine the dipoles in a pancake geometry were essentially sort of perpendicular to the direction of the dipoles. Then, of course, the dominant interaction is the one where they are in a repulsive configuration. But still, if you are in the weakly confined situation where the length of the confinement is which is on the micron scale, is much larger than the typical dipolar lengths, which are, say, 100 mu Bohr, 100 A Bohr, is then there's still the possibility that they can be on top of each other and they can interact attractively. And you can find out that, I mean, in this pancake geometry, the condition for stability is sort of weaker than for a homogeneous 3D situation. You only require that there's a positive short-range scattering length. Now, how did people sort of observe, or what is observed sort of in these dipolar gases? So there are essentially three groups. Tilman Pfau in this group in Stuttgart. There's Francesco Fallaino, and I mentioned Lauriane Chaumin here. She did a PhD with Jean a few years ago in Innsbruck, and Giovanni Modugno and collaborators in Pisa. And the typical systems are dysprosium or erbium gases, Bose gases in traps, which are, the figure I took from one of the papers of Giovanni Modugno, elongated along sort of a weak axial direction. The dipoles are oriented along C here. And the dipolar length is something that is sort of given by your, of course, strength of the dipole moment. What you can tune in the system is the short-range scattering length with a Feschbach resonance. And in a way, you can make the dipolar interaction stronger by reducing the short-range scattering length. And so now I show a figure which comes from a paper by Herdkorn et al., which was published earlier this year from Tilman Pfau's group, where they looked at in situ density profiles of such dipolar gases in these elongated traps as for different short-range scattering length. If the short-range scattering length is above the dipolar length, here this one, you have essentially a reasonably homogeneous BEC, then at whatever below 100, so it's just pretty fine-tuning of scattering lengths. This system sort of breaks up in a series of small domains, and then eventually, sort of, if you make the short-range scattering length too small, then I mean these domains are separated by sort of less density, so the density contrast becomes stronger and stronger, and so eventually this is called the regime of isolated droplets, where no phase coherence can be established along the direction here shown here. And here there is, in a way, the densities now for different individual shots, and what is done actually in this experiment is that, I mean, if you measure the densities, Fourier transform them in an average over many shots, what you can do is essentially you can measure an average of delta n squared and therefore get the static structure factor. What is shown here is the static structure factor actually normalized. So this, as for different short-range scattering lengths as a function of the longitudinal momentum. Of course, the density modulation is easiest along this axial direction, so it develops along this direction. And what you see is for strong short-range scattering lengths, that's sort of a pretty, I mean, doesn't really show much structure. But then a peak appears in the static structure factor, and then sort of eventually, well, disappears again and is shifted sort of to weight at higher momentum, where the momentum here, as you see, is inverse micron. You will see the scale is set by the transverse confinement length LC. And from these data, which you can roughly extract an effective excitation energy, E of Q, by using the finite temperature generalization of the single mode approximation of Feynman, which compared to the zero temperature expression I given before has this thermal factor or enhancing. And if you use this static structure factor to infer an excitation spectrum, you get sort of this rough behavior. I mean, it's not, of course, very sort of sharp, not as nice as you have in helium, but you get something where you see there is a excitation spectrum which for strong short-range scattering lengths goes up, then starts to develop some minimum, but at this point where sort of this supersolid phase appears is finite. It's, however, only of the order of 20 hertz. The temperature of these systems is 20 nanokelvin, so actually the ratio of the roton gap is much less than kT. So in a way, this thermal factor is huge. It's 50 or 100 or something like that. So of course, it would be nice if this was not so large. So now, such earlier experiments along this line have been done sort of with Bragg scattering by the Innsbruck group, Petter et al. And they also have something that, I mean, okay, I find striking that although, of course, this is a very different system, it has also attractive interactions, but it also shows that the transition, or it exhibits a situation where the transition to the supersolid phase with a finite density modulation appears at a finite value of this sort of roton minimum. And so the question is, I mean, can one qualitatively understand this a bit better, and then also sort of draw some conclusions for the modes. Now, the question is, I mean, what is a necessary condition for having a roton minimum? And sometimes, I mean, you might say, well, maybe we need some attractive interaction. That's not true. I mean, for purely repulsive interactions, you can have a roton minima. Just take a repulsive sort of square potential that has a negative Fourier transforming interaction. If you do Bogoliubov theory for a dilute BC, you get sort of a roton structure. And here, in a two-dimensional situation for weakly confined dipoles, of course, for distances which are much larger than this transverse confining length, you have repulsive 1 over r cubed interaction. But sort of the formal Fourier transform of that is negative, is minus mod q. And of course, you need some, and so if you just take the full dipolar-dipole interaction, Fourier transform it, you get something which starts here linear and then fades off to a negative value, and you need some positive scattering length to make this stable. If you do with such a potential interaction potential Bogoliubov theory, of course, you get a Roton minimum, and you get structure factors which you can easily get here in the regime of interest, which at zero temperature look like this, and have at zero temperature in the regime where the scattering length, short-range scattering length, and this dipolar length are of the same order, have peaks on the order of, say, between 1.5 and 2. So there's a rather, in a way, shallow maxima which appear here. And what we have done here then with Johannes Hoffmann, and this is something which was quite a surprise to me, is that we looked at the, in a way, phase diagram or stability diagram of such a system. This is a two-dimensional system with dipolar interactions worked out within this so simple Bogoliubov approximation. There's and you plot it in terms of this effective G tilde, which appears in 2 dimensions as a difference between the short-range scattering length and the dipolar length, which, okay, in the regime of interest is negative as a function of the strength of the dipolar interaction. And what you find is that there's a regime, of course, where this system has a nice uniform superfluid phase, but then there is a line, which I indicated here in blue, which is formally the Roton instability, where the static structure factor would diverge and the Roton minimum would approach 0. But in a way, before that, you actually, if you apply the criterion which, I mean, okay, worked for repulsive interactions in 2D quantum fluids, and say, I mean, there's a transition to a state with density, finite density modulation when the critical value of the static structure factor has reached the order of 1.7 or something like that, then you see that this green line essentially agrees with the appearance of a Roton minimum. So the conclusion from this simple exercise is that basically at the point where the Roton minimum starts to develop, this system already shows, I mean, it doesn't really go deep into that regime. The system already goes into a supersolid phase with a finite density modulation. Of course, Hansen-Verlet and all these things, this is not a theory of the transition. And the unfortunate situation now is that, I mean, I don't think anyone has a real microscopic theory of these systems and the transition to the supersolid phase that appears here. I mean, there is some nice results which you can obtain from using Gross-Pitaevsky approximations. You get some critical value which agrees with experiment, but I mean, it's not sort of a systematic way of dealing this. So we are far from a microscopic understanding of this transition in terms of what we have, say, in helium-4, where we know precisely. And in particular, of course, this transition is in the end driven by these attractive interactions. And the length scale at which this Q sub 0, which appears here, is set by the transverse confining length. So there is no, it's not set by the average interparticle spacing. So we are not going into a commensurate Mott insulator. And so, okay, this is a somewhat unfortunate situation that in a way on a microscopic level, this is not so well understood. But I think there are a few things which I believe can be understood in this context without going to the microscopic system on purely general grounds. And now I come back to this point I discussed before, that in a way, in a situation where there's a strong modulation of the density, the superfluid fraction is much less than 1 if the modulation of the density is small. Does that show up somehow? Well, it shows up in the Bogoliubov sound velocity. This was done, I mean, here I'm referring to a paper by Chiara Minotti and Sandro, who is sitting in the audience, 15 years ago, who actually, after the BCs in optical lattice were discovered, said, okay, let's calculate the sound velocity of that system in the optical lattice. And of course, I mean, you get a Bogoliubov mode of superfluids in an optical lattice. So very simply, of course, a bunch of harmonic oscillators with a spectrum that is linear in Q. And sort of the question is, I mean, what is this velocity of sound? Now you can actually, of course, I mean, you can do this sort of in some weak coupling description, but you can actually, on a completely general way, show that this velocity of sound actually is directly, or squared, is directly proportional to the superfluid fraction. So this formula, this is, in a way, it's essentially, I mean, you can get it essentially from a hydrodynamic, the superfluid hydrodynamics in this presence of an optical lattice, where sort of this K is just sort of the, in a way, overall compression. And in particular, if you go to weak interactions, where the condensate fraction is 1, the superfluid fraction is tiny, and you see that because the corresponding sound velocity is also tiny, because it turns out the sound velocity is just sort of the mean field interaction divided by the band mass. And the band mass is, I mean, if you have a deep lattice, the band mass is large. So this is, in a way, you have a Goldstone mode, of course, because there's broken sort of gauge symmetry, because this is a superfluid. If the state would not be superfluid, of course, you would not have a linear propagating mode in an external lattice. But note, of course, here, because the translation invariance I've broken externally, the eternal lattice is given. There's only a single Goldstone mode. There's not two. Now, if you recall this picture here of this supersolid phase along this axial direction of the optical lattice, it's essentially what I call a mass density wave. And the question is, I mean, can one derive the spectrum of Goldstone and hydrodynamic modes in a situation where I have superfluidity coexisting with a periodic order which only goes along one direction? Of course, in the dipolar gases, this unidirectional nature of the ordering is due to the axial trap. Here I sort of, in a way, abstract from this and say, well, I assume something what I call a superfluid smectic, a phase where I have a fluid, say, in the plane, which has a density modulation on top of it, if I assume that system is not only sort of, in a way, it has not only long-range order in the density, but is also superfluid, what are the modes? Now, this is, in a way, a description of this system is, in a way, a generalization of what people have done here in Orsay 40 years ago or 50 years ago. De Gennes had a huge, of course, liquid crystals. This is a superfluid liquid crystal phase. And De Gennes has actually developed a description of sort of the order in the system where you say, okay, you have the equilibrium density has, of course, a discrete set of Fourier modes, which is set by the given wave vector corresponding to this modulation. And if you want to describe density modulations, you can describe it by what people call the layer phase U. And this layer phase, if you multiply it with Q0, you see is like an angle. The angle ranges between minus pi and pi, because, I mean, going 2 pi further doesn't sort of change this expression. And so it was actually De Gennes in '72 who realized that the order in these smectics, at that time classical smectics, is sort of similar to or equivalent to, I mean, the order which we have in superfluids. And now the question is, I mean, what are sort of vibrations of this lattice do? If you think usually sort of, if you look in textbooks about lattice vibrations, then the density is average density to lowest order times the divergence of a deformation field. That's the usual thing. But that assumes there is no defects around. Here in this system, the total density fluctuations, you can change the density here either by sort of changing, of course, the average distance between these stripes, but you can also change it at a given fixed distance between the stripes by transporting particles between these layers. That's what I call the defect density. And it actually it's important that, I mean, you need both contributions, and then you just do essentially thermodynamics. I mean, hydrodynamics is as general as thermodynamics. You write the entropy density or differential of the entropy as a function of the conserved variables. Conserved is energy, mass, and momentum. These are in 2 dimensions 4 variables because momentum has 2 components. And then I have 2 broken symmetries, superfluidity and the lattice modulation. And there's conjugate fields here, this is this H here, and the superfluid density. So there's 4 conservation laws and 2 scalar broken symmetries, which by simple counting gives 6 hydrodynamic modes. The counting is simple here because you're not breaking time reversal invariance. These things were worked out in general, sort of, I mean, superfluids, hydrodynamics of smectics and all other liquid crystals was worked out by Paul Martin, actually here during a sabbatical at Orsay in '72. And this, you can show that, I mean, 2 of those 6 modes are Goldstone modes. They always appear in pairs. They're linear dispersing, so there's 2 velocities. And there's 2 diffusive modes which describe heat and shear diffusion. Note that heat diffusion appears here as a separate mode because of the periodic modulation of the density. If there was no periodic modulation of the density, heat would not diffuse, but would propagate. And then basically, what are these conjugate fields? The superfluidity is, I mean, the current density is the usual rho s times Vs, that's what we know. But in a Galilean invariant system, there's the minus Vn. And usually, if you think about superfluids, the normal at low enough temperatures, there's no normal fluid. We can forget about this. But here not. Then there's still because of the finite density modulation, there's a normal fluid part, if you wish, at 0 temperature. And the normal velocity here is just the time derivative of this displacement field. I mean, that was proven in quite general terms by Damson in 2005. You need, so there's one parameter, the stiffness of the superfluid, the other parameter, the stiffness of this density order, which is called the layer compression modulus. This is a notion which goes back to the liquid crystal people. And then you can work out analytically the mode velocities. And you actually can show that, in a way, the usual first and second sound, the usual second sound is not there. I mean, entropy drops out at low enough temperatures because you have a finite normal fluid density at 0 temperature. And one of these, the one with the C2, is the defect density mode of Andreev and Lifshitz, and the other one is sort of the usual Bogolyubov mode. And you can, in terms of these constants, compressibility, this layer compression modulus from this order, and the superfluid fraction or the normal fraction, you can work out everything analytically. Now, of course, I mean, this is an idealized model. I think it gives a pretty nice description of sort of, I mean, what's going on, and explains also this story with the defect diffusion. But of course, quantitatively, it's not, we are not having a uniform system, and we are not measuring so far really properly sound velocities. But I show a figure which I did steal from a paper by the PISA group and Sandro Stringari, sort of here, who has basically explained this in terms of a time-dependent Gross-Pitevsky equation, solving this in the trap. What you see here, there's an axial breathing mode in this along this trap, which in the BC has a frequency which is 3/2 times the axial, the trap frequency. But then in the supersolid, it splits into one which goes up and one which goes down. And I think this is sort of, in a way, the finite size version of these 2 modes. The one goes up because basically with the appearance of this periodic density modulus, there's this compression, layer compression modulus comes in, and the other one goes down because the normal fluid density actually increases more strongly than this B. And so in a qualitative manner, you can say the fact that you get sort of two well-defined propagating modes now because of this finite density modulation is something that is reflected in this spectrum of two modes in a trap. So I'm essentially finished and would like to conclude sort of with a few general statements. I think one should be extremely careful about talking about superfluids and say precisely define what one means about it. And one should in particular distinguish supersolids in a genuine way from spatially modulated superfluids, which like you have in the vortex lattice, and in particular in a, I will perhaps, if you can go a bit further on this in the discussion session if you wish, the phase diagram is of course very different. For genuine supersolids, I've argued, well, following essentially Andreev and Lifshitz, that you need a finite defect density in the ground state. I mean, this is a point that was made a long time ago already also by Prokofiev and Zwisterov. And essentially, it's not a real sort of commensurate solid, but what you need is something, a mass density wave, which is incommensurate. There's no question about the number of particles per lattice spacing being an integer number. And you get to such a phase in dipolar gases in these elongated traps. Generically, and I don't know any exception to be honest, the transition from a fluid phase to a phase with a finite density modulation is always first order. I don't know of any continuous transition in this direction. And so I say that the rotor instability is always preempted. And the final point is that if you have a supersolid, then you get this wave-like propagation of defects, which in a way is a bit like second sound, which exists now as a proper motion at well-defined mode at zero temperature, where the motion of the lattice sort of is playing the role of the normal fluid fraction. Okay, sorry for taking a full hour, but I hope it wasn't too long, and thank you for your attention.